The universe is vast, mysterious, and filled with questions that intrigue scientists and enthusiasts alike, particularly when it comes to the fundamental forces that govern everything from the smallest particles to the largest galaxies. One of the most exciting areas of research in modern physics is the quest to discover new fundamental forces beyond the four we already know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The idea of uncovering new forces has tantalized researchers for decades, prompting questions about how these forces could reshape our understanding of the universe and the very fabric of reality itself. Could there be forces that operate at scales we have yet to comprehend? Some scientists speculate that there might be a fifth fundamental force, perhaps linked to dark matter or dark energy, which could explain the mysterious acceleration of the universe's expansion. The search for such forces often leads researchers to high-energy particle collisions, like those conducted at the Large Hadron Collider, where particles are smashed together at incredible speeds, creating conditions similar to those just after the Big Bang. These experiments could reveal new particles or interactions that hint at additional forces. As we explore the potential for new forces, we also consider their implications for our understanding of gravity. Could modifications to our current theories provide insights into gravitational anomalies observed in galaxy rotations, or even lead to a unified theory that reconciles general relativity with quantum mechanics? Such a theory could radically change our perspective on how forces interact and how they shape the cosmos. Furthermore, researchers are investigating the role of symmetry in nature as it plays a crucial part in governing the known forces. The exploration of symmetries could unlock pathways to discovering previously unknown interactions. Then there's the intriguing possibility of forces that might be exerted by dimensions beyond our familiar three-dimensional space. String theory, for instance, posits the existence of additional dimensions that could harbor unique forces, impacting the fundamental interactions we observe. This idea challenges our conventional understanding and invites us to think beyond the limits of our current scientific models. Moreover, the concept of time itself could be intertwined with new fundamental forces. Some theories suggest that time may not be a constant, but instead could be influenced by the interactions of forces at a deeper level. This speculation invites questions about causality and the nature of reality. As we delve deeper into the quantum realm, the strange behaviors of particles suggest that there may be forces operating in ways we cannot yet fully comprehend. Quantum entanglement, for example, rages throughout history. Humanity's fascination with the cosmos has been a driving force behind exploration, scientific inquiry, and philosophical thought, as ancient civilizations, like the Babylonians and Egyptians, looked to the night sky, using the stars for navigation, agriculture, and religious purposes, laying the groundwork for astronomy as we know it today. The Greeks, particularly philosophers such as Aristotle and Ptolemy, contributed significantly to our understanding, proposing models of the universe that, while incorrect, sparked further inquiry and debate about the nature of celestial bodies. The Middle Ages saw a blend of ancient knowledge with Islamic scholarship, as astronomers like al-Khwarizmi and al-Battani preserved and expanded upon Greek texts, introducing new numerical methods and observations that would later influence the European Renaissance. The Copernican revolution in the 16th century marked a pivotal shift in our understanding of the universe, as Nicolaus Copernicus proposed a heliocentric model, placing the Sun at the center instead of the Earth, challenging long-held beliefs and igniting a scientific revolution. This shift was further advanced by the work of Johannes Kepler, who formulated his laws of planetary motion, demonstrating that planets move in elliptical orbits, not perfect circles, and Isaac Newton's law of universal gravitation, which explained the forces governing celestial bodies. The invention of the telescope in the early 17th century, by figures such as Galileo Galilei, allowed for unprecedented observations of the night sky, revealing moons orbiting Jupiter and the faces of Venus, providing concrete evidence that supported the heliocentric model. As the centuries progressed, advances in technology and mathematics continued to refine our understanding of the universe, with 19th century physicists like James Clerk Maxwell developing theories that unified electricity, magnetism, and light, while Albert Einstein's theory of relativity in the early 20th century revolutionized our perception of space, time, and gravity, revealing a much more complex and interconnected universe than previously imagined. This era also saw the advent of quantum mechanics, which introduced the idea that at the smallest scales, particles do not behave in ways that align with classical physics, prompting deeper inquiries into the fundamental nature of reality and the universe. The launch of the first artificial satellite, Sputnik, in 1957, marked the beginning of the space age, allowing for new perspectives of Earth and the cosmos, leading to the exploration of the Moon, Mars, and beyond, as missions like Apollo 11 brought humans to the inner realm of physics. Are four fundamental forces that govern the interactions we observe in the universe. Each force plays a crucial role in shaping the behavior of matter and energy, and understanding these forces is essential to grasping the workings of the cosmos. The first force is gravity, which, although it seems weak compared to the other forces, has an infinite range and is always attractive. It governs the motion of planets, stars, galaxies, and even light, pulling objects toward one another, and it is described by the general theory of relativity proposed by Albert Einstein, which reveals how mass curves space-time, resulting in what we perceive as gravitational attraction. The second force is electromagnetism, a much stronger force than gravity, which acts between charged particles. This force is responsible for electricity, magnetism, and light, and it governs a wide array of phenomena, from the behavior of atoms and molecules to the formation of chemical bonds, and it is described by the theory of quantum electrodynamics, which explains. The third force is the weak nuclear force, which is responsible for processes such as beta decay, a type of radioactive decay that occurs in certain unstable atomic nuclei. This force operates at very short ranges, on the order of a fraction of the diameter of a proton, and it plays a critical role in the nuclear processes that power the Sun and other stars, enabling fusion to occur. Finally, the fourth fundamental force is the strong nuclear force, which is the strongest of all forces. Yet it operates at an incredibly short range, less than the diameter of an atomic nucleus. This force binds protons and neutrons together within the nucleus, overcoming the electromagnetic repulsion between positively charged protons, and it is described by the theory
of quantum chromodynamics. Each of these forces has unique properties and interactions, and they are unified in various ways in advanced theoretical frameworks, such as string theory, which seeks to explain the fundamental nature of reality and how these forces might be connected at high energies. Understanding these forces not only helps us to comprehend the fundamental structure of matter, but also allows us to explore the vast mysteries of the universe, from the smallest particles to the largest cosmic structures. Throughout history, discoveries in physics have profoundly shaped our understanding of the fundamental forces that govern the universe, starting with Sir Isaac Newton's groundbreaking work in the 17th century, where he formulated the laws of motion and universal gravitation, introducing the idea that every mass exerts an attractive force on every other mass. This was a revolutionary concept, as it provided a mathematical description of gravity, allowing us to comprehend not only the motion of objects on Earth, but also the orbits of planets and moons. Newton's work set the foundation for classical mechanics, which dominated our understanding of physics for centuries, and his ideas were further solidified by
experiments, such as those conducted by Galileo, who studied the motion of falling bodies and demonstrated that objects fall at the same rate, regardless of their mass, reinforcing the principles of gravity. Fast forward to the 19th century, and we encounter James Clerk Maxwell, whose formulation of electromagnetic theory brought together electricity and magnetism, revealing that they are interconnected aspects of a single force. This unification led to the understanding that light is an electromagnetic wave, fundamentally altering our comprehension of energy and its propagation through space. Maxwell's equations not only explained the behavior of electric and magnetic fields, but also laid the groundwork for modern technologies such as radio and television, showing how theoretical physics can lead to practical applications that transform society. In the early 20th century, Albert Einstein introduced the theory of relativity, which fundamentally changed our perception of space and time. His famous equation reveals the profound relationship between mass and energy, suggesting that mass can be converted into energy and vice versa. This principle is not just theoretical. It has practical implications. As seen in nuclear reactions, where tiny amounts of mass yield vast amounts of energy, Einstein's work also led to the understanding of gravity as the curvature of space-time, a radical shift from Newton's view, which has been confirmed by numerous experiments, including the observation of gravitational waves, predicted by Einstein and detected a century later. In the mid-20th century, the development of quantum mechanics introduced a new layer of complexity to our understanding of fundamental forces. As physicists like Niels Bohr and Werner Heisenberg explored the behavior of particles at the atomic and subatomic levels, the quantum theory, particles can exist in multiple states simultaneously, leading to phenomena such as superposition and entanglement, which challenge our classical intuitions, while quantum mechanics primarily deals with the formulation of the four known fundamental forces: gravitational, nuclear, and strong nuclear, has been shaped by the contributions of many brilliant scientists throughout history, each of whom brought unique insights that helped us understand the universe at a deeper level. Starting with gravity, Isaac Newton, in the 17th century, laid the groundwork with his law of universal gravitation, which described how masses attract one another, providing a mathematical framework that explained the motion of celestial bodies. And although Newton's work was groundbreaking, it was Albert Einstein, in the early 20th century, who revolutionized our understanding of gravity with his general theory of relativity, proposing that gravity is not just a force, but a curvature of space-time caused by mass. Moving on to electromagnetism, we must mention James Clerk Maxwell, whose set of equations, known as Maxwell's equations, unified electricity and magnetism into a single theory, showing how electric and magnetic fields interact and propagate as waves, which was a fundamental advancement. Later, the work of Richard Feynman and other physicists in the 20th century further developed quantum electrodynamics, explaining how light and matter interact on a quantum level, essentially expanding our understanding of electromagnetic forces. In the realm of nuclear forces, the weak nuclear force, which is responsible for processes such as radioactive decay, was primarily explored through the work of Enrico Fermi, who developed the Fermi theory of beta decay in the 1930s. His contributions were crucial in understanding how subatomic particles interact via the weak force, alongside the later work of Steven Weinberg and Abdus Salam, who in the 1970s developed the electroweak theory, which unified the weak nuclear force and electromagnetism into a single framework, showing how these two interconnected at high energy levels. The strong nuclear force, which binds protons and neutrons in atomic nuclei, was significantly advanced by the work of several physicists, including Hideki Yukawa, who proposed the concept of mesons as This idea was pivotal in understanding how particles interact at extremely small distances, and it laid the foundation for the development of quantum chromodynamics, a more complete theory that describes the strong interaction. This theory was further refined by the contributions of many others, including David Gross, Frank Wilczek, and H. David Politzer, who were awarded the Nobel Prize. The development of quantum mechanics has had a profound impact on our understanding of forces in the universe, revolutionizing the way we perceive interactions at the most fundamental levels. Before quantum mechanics emerged in the early 20th century, classical physics, with
its deterministic view, dominated the scientific landscape, providing a solid foundation for understanding forces, such as gravity and electromagnetism, through equations and predictable behaviors. However, as scientists began to explore the behavior of particles at atomic and subatomic scales, they discovered that the classical laws were inadequate, leading to the birth of quantum mechanics, which introduced a probabilistic nature to physical phenomena. One of the most significant contributions of quantum mechanics is its explanation of the electromagnetic force, which is crucial for the interaction between charged particles. Quantum electrodynamics, a field within quantum mechanics, describes how light and matter interact, revealing that particles, like electrons, exchange virtual photons, thus facilitating electromagnetic interactions. This understanding has not only deepened our knowledge of forces, but also has practical applications, such as in the development of lasers and semiconductor technology. Moreover, quantum mechanics has reshaped our understanding of the strong and weak nuclear forces, the fundamental forces that govern the interactions within atomic nuclei. The strong nuclear force binds protons and neutrons
together, while the weak nuclear force is responsible for processes like beta decay. Through the framework of quantum field theory, scientists have been able to describe these forces in terms of particle exchanges, such as gluons for the strong force and WNs. This particle exchange concept has allowed physicists to create a unified model that explains how these forces operate on a fundamental level, providing a clearer picture of how matter behaves in extreme conditions, such as those found in stars and during particle collisions in accelerators. Additionally, the development of quantum mechanics has also led to the exploration of gravity through the lens of quantum theory. Although a complete quantum theory of gravity remains elusive, researchers have ventured into theories like string theory and loop quantum gravity, which attempt to reconcile general relativity with quantum mechanics. These efforts have the potential to unveil new insights into how gravity operates at the smallest scales, possibly leading to a deeper understanding of phenomena like black holes and the fabric of space-time itself. Furthermore, quantum mechanics has introduced concepts like entanglement and superposition, which
challenge our traditional notions of locality and separability in forces. For instance, when particles become entangled, the state of one particle can instantaneously affect the state of another. The discovery of gravity as a force, particularly through the work of Sir Isaac Newton in the 17th century, revolutionized our understanding of space and time in profound ways, fundamentally altering the course of science and our comprehension of the universe. Before Newton, the prevailing view of motion and celestial bodies was largely influenced by Aristotle's ideas, which suggested that celestial objects moved in perfect circles, governed by different laws than those that applied to earthly objects. However, Newton introduced a groundbreaking concept, which stated that every mass attracts every other mass through a force he termed gravity. This realization not only provided a mathematical framework to describe the motion of objects on Earth, but also extended to the movements of planets, moons, and stars in space. The implications of Newton's law of universal gravitation were vast, as it suggested that the same force that caused an apple to fall from a tree also governed the orbits of the planets around the sun. This interconnectedness
illuminated the idea that the universe operates under consistent laws, regardless of the scale or location, which was a significant shift from the previously held notions of separate realms for earthly and celestial phenomena. Gravity became the key to understanding how celestial bodies interacted, leading to insights into the orbits of planets, the behavior of comets, and even the formation of galaxies. This also laid the groundwork for future scientific advancements, notably influencing Albert Einstein's theory of general relativity in the early 20th century. Einstein expanded upon Newton's ideas, proposing that gravity is not merely a force, but a curvature of space and time caused by massive objects. His revolutionary perspective suggested that massive bodies like planets and stars warp the fabric of space-time around them, creating a sort of dip that causes other objects to move towards them. This understanding of gravity as a geometric property rather than just a force alone altered our perception of the universe, allowing us to view space and time as interconnected dimensions that influence one another. With this new lens, the notion of time itself changed. It was no longer a constant, unchanging backdrop against which events unfold, but rather a dynamic entity that could stretch and warp in the presence of gravity. This leads to fascinating phenomena like time dilation, where time moves slower in stronger gravitational fields, a concept that has practical implications, especially in the context of satellites in orbit around the Earth. The Global Positioning System, GPS, for instance, must account for these relativistic effects to provide accurate location data, illustrating how deeply intertwined our understanding of gravity is. Theoretical frameworks in the study of space and the universe provide a structured way to understand complex phenomena. They serve as essential tools for scientists and researchers, guiding their inquiries and shaping their interpretations of data. One of the most prominent frameworks is the theory of general relativity, proposed by Albert Einstein in 1915, which describes how gravity fabric of space-time. It revolutionized our understanding of gravity, showing that massive objects like planets and stars warp space-time, leading to the phenomenon we observe as gravity. In contrast, quantum mechanics offers a different perspective. Smaller scales, it introduces concepts like wave, particle duality, and uncertainty, which challenge our classical understanding of physics. Together, these two frameworks form the foundation of modern physics. Yet they remain fundamentally incompatible in many aspects, prompting scientists to reconcile the differences between them. String theory and loop quantum gravity are among the leading candidates for such a unifying framework. String theory suggests that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. It posits the existence of multiple dimensions beyond the familiar three dimensions of space and one of time, which could explain some of the mysterious phenomena observed in the universe. On the other hand, loop quantum gravity attempts to quantize space, time itself, proposing that space is composed of discrete units, much like the pixels in a digital image. This framework aims to bridge the gap between general relativity and quantum mechanics, yet it is still a work in progress. The study of cosmology, which examines the large-scale structure and evolution of the universe. These theoretical frameworks, using them to interpret observations from powerful telescopes and space missions, for example, the cosmic microwave background radiation, which is the afterglow of the Big Bang, provides a wealth of information about the early universe, and theoretical models help scientists understand its implications. Another aspect of theoretical frameworks in space science is their role in guiding experimental and observational efforts. Researchers develop hypotheses based on existing theories and then design experiments or observations to test these ideas. If the results align with the predictions, support. If not, it may need to be revised or replaced. This iterative process of hypothesis and testing is crucial for advancing our understanding of the universe. As new technologies emerge, they enable scientists to explore previously inaccessible realms, leading frameworks, for instance, advancements in artificial intelligence in the quest to understand the universe. Scientists have long recognized 4 fundamental forces: gravity, electromagnetic forces, the strong nuclear forces, and the weak nuclear force. However, the idea that there might be additional fundamental forces lurking beneath the surface of our current understanding has captured the imaginations of physicists and cosmologists alike. One prominent theory that suggests the existence of additional forces is string theory, which posits that fundamental particles are not point-like objects but rather tiny vibrations. In string theory, the various vibrational modes of these strings correspond to different particles and forces, which means that there could be multiple hidden dimensions, and in those dimensions additional forces could exist, influencing the behavior of our universe in ways that we have fully comprehend. Another fascinating proposal is the concept of extra dimensions, which is often explored within the framework of theories like Kaluza, Klein theory, an early attempt to unify gravity and electromagnetism. This theory suggests that if additional spatial dimensions exist, they could host new forces that might interact with the familiar 4 forces we know. Moreover, there is a growing interest in the idea of modified gravity theories, such as MOND, or modified Newtonian dynamics, which attempts to explain the observed rotation curves of galaxies without invoking dark matter. These theories propose that gravity itself could behave differently, under certain conditions, hinting at a fundamental modification in how we understand gravitational interactions, and suggesting that there could be a deeper connection or additional forces at play. Additionally, the concept of quantum gravity, which seeks to merge quantum mechanics with general relativity, also opens the door to the possibility of new forces. Researchers in this field are investigating how quantum fluctuations might introduce new interactions, potentially leading to forces that have yet to be observed. There is also a hypothesis known as the 5th force, which has surfaced in various experimental contexts, raising questions about interactions that might not fit neatly into the existing framework of fundamental forces. For example, recent experiments have suggested anomalies in particle behavior that could indicate the presence of a 5th force, one that would operate under specific conditions or at particular scales, leading to exciting implications for our understanding of particle physics and cosmology. Furthermore, some theories in the realm of unification, like grand unified theories, GUTS, propose that at extremely high energies, the 3 gauge forces, strong, weak, and electromagnetic, could unify into a single force and perhaps even include additional interactions that we have yet to discover. String theory, a groundbreaking framework in theoretical physics, proposes that the fundamental building blocks of the universe are not point, like particles as traditionally thought, but rather tiny, vibrating strings. These strings can oscillate in different modes, and the particular vibration of a string determines the type of particle it represents, whether it's an electron, a quark, or even a graviton, the hypothetical particle that mediates gravity. Now, as string theory seeks to unify all fundamental forces in nature, including gravity, electromagnetism, and the strong and weak nuclear forces, it implies that there could be additional forces at play, forces that we have yet to discover. The theory suggests that our familiar forces arise from the vibrational patterns of strings. But there might be other, hidden dimensions beyond our three-dimensional perception of space and one-dimensional perception of time. In string theory, these extra dimensions could provide a fertile ground for new forces. For instance, if there are additional dimensions curled up in ways that we cannot easily perceive, they could influence the behavior of strings, leading to the emergence of new interactions that are not accounted for in the standard model of particle physics. This idea posits that the configuration and shape of these extra dimensions can dictate how strings vibrate, thereby resulting in new forces that could manifest under specific conditions. Furthermore, some versions of string theory, such as M theory, suggest that our universe might be just one of many, each with its own set of physical laws and forces. The implications of new forces emerging from string theory are profound. They could potentially help explain phenomena that remain puzzling, such as dark matter and dark energy, which together make up most of the universe's mass, energy content, but have yet to be fully understood. If string theory is correct, the new forces could interact with ordinary matter in subtle ways, leading to observable effects that we have yet to measure. Moreover, researchers are actively exploring the possibility that these forces could be detected in high-energy particle collisions, such as those occurring at the Large Hadron Collider, where energies are sufficient to probe these hidden dimensions and the corresponding new forces. As scientists continue to study string theory, they aim to not only understand the fundamental structure of the universe, but also to identify the potential signatures of these new forces. This quest for knowledge is exhilarating, as it opens up a realm of possibilities, where the very fabric of reality could be different from what we perceive, and where new forces might interact with the known forces in unification theories, at their core aim to explain how the fundamental forces of nature, which include gravity, electromagnetism, weak nuclear force, and strong nuclear force, are interconnected, and this pursuit has profound implications for our understanding of the universe. These theories suggest that, at very high energies, these forces may not be distinct, but rather different manifestations of a single underlying force. For example, in the early universe, conditions were so extreme that the distinctions between these forces might have blurred, leading to the idea that they were all unified. This concept comes from the realm of theoretical physics, particularly string theory and grand unification theories, which propose that all forces could be described by a single framework. String theory, for example, posits that the fundamental particles we observe are actually tiny, vibrating strings, and the different modes of vibration correspond to different particles. This idea not only suggests a deeper connection among the forces, but also opens the door to understanding how gravity can be reconciled with quantum mechanics, which has been a significant challenge in physics. By exploring these unification theories, scientists hope to uncover a theory of everything, which could provide insights into the very fabric of the universe, including the nature of dark matter and dark energy, which together make up a large portion of the cosmos. Moreover, the implications of unification theories extend to our understanding of the early universe, particularly during events such as the Big Bang, where the energy levels were so high that the forces may have been unified. This leads to questions about the conditions that existed just after the Big Bang, and how the universe transitioned from that singular state to the diverse cosmos we observe today. If we can understand how these forces behaved in the early universe, we might gain insights into cosmic inflation, the rapid expansion that occurred shortly after the Big Bang, and how it shaped the large-scale structure of the universe. Additionally, exploring unification theories could impact technological advancements as well. Understanding the fundamental forces and their unification could lead to breakthroughs in energy generation, materials science, and even quantum computing, as these theories may reveal new ways to manipulate energy and matter at fundamental levels. The quest for unification is not just about theoretical physics. It also has practical implications that could transform our technological landscape. The search for a unified theory is ongoing, with many physicists conducting experiments at particle accelerators, such as the Large Hadron Collider, to test predictions made by these theories. Discoveries in this field could either quantum gravity, a fascinating and complex area of theoretical physics, challenges our current understanding of forces in several profound ways. Traditionally, we understand forces through two major frameworks. General relativity, which describes gravity as the curvature of space-time caused by mass, and quantum mechanics, which effectively explains the behavior of particles at the smallest scales, such as atoms and subatoms. However, when we attempt to merge these two theories, we encounter significant difficulties, primarily because general relativity operates on a macroscopic scale, while quantum mechanics excels at the microscopic level, leading to a mismatch in how we perceive and describe forces. One of the core issues is that, in general relativity, gravity is not treated as a force in the traditional sense, but rather as the geometry of space-time itself. Objects move along paths determined by this curvature, which means that gravity doesn't have a force carrying particle, unlike the other fundamental forces, such as electromagnetism, which is mediated by photons, or the strong and weak nuclear forces. mediated by gluons and was bosons, respectively. This absence of a graviton, a hypothetical particle that would mediate gravitational interactions in a quantum framework, leads to challenges when trying to apply quantum principles to gravity. Moreover, at the quantum level, the concept of space-time itself becomes problematic. Quantum mechanics relies heavily on probabilities and uncertainties, as described by the Heisenberg uncertainty principle, which suggests that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. If we take this into account, we start to wonder what the very fabric of space-time looks like when viewed through a quantum lens. Some theorists propose that space-time might be discrete at the smallest scales, leading to a foamy structure, but this stands in stark contrast to the smooth continuum described by general relativity. Another challenge posed by quantum gravity is related to the phenomenon of black holes. According to general relativity, when objects collapse under their own gravity, they can form black holes, regions of space-time, where gravity is so strong that nothing, not even light, can escape. However, when we apply quantum mechanics to black holes, we encounter the so-called information paradox, which raises questions about whether information that falls into a black hole is lost forever, violating the principle of quantum information conservation. This paradox has sparked intense debate in the physics community and suggests that our current theories may be incomplete. Additionally, the search for in-particle physics. The fundamental forces are the interactions that govern how particles behave and interact with one another, and these forces play a crucial role in shaping the universe as we know it. There are 4 fundamental forces in nature. Gravitational, nuclear and weak nuclear forces, and each of these forces has unique characteristics and operates at different scales. The gravitational force, for instance, is the weakest of the 4 forces, but it acts over long distances and governs the motion of planets, stars, and galaxies, influencing the structure of the universe on a grand scale. In contrast, the electromagnetic force is responsible for the interactions between charged particles, and it governs phenomena such as electricity, magnetism, and light. This force is much stronger than gravity and operates at the level of atoms and molecules, playing an essential role in chemistry and the formation of matter. Moving on to the strong nuclear force, this force is the strongest of the 4, and it acts over extremely short ranges, binding protons and neutrons together in atomic nuclei. Without this force, atomic nuclei would not be stable, and matter as we know. This strong force is mediated by particles called gluons, which are exchanged between quarks, the fundamental building blocks of protons and neutrons. On the other hand, the weak nuclear force is responsible for processes like beta decay, and an antineutrino. This force is crucial for the nuclear reactions that power stars, including our Sun, and it operates at very short ranges, similar to the strong force, but it is weaker than both the strong and electromagnetic forces. In the realm of particle physics, the relationship between these fundamental forces and particles is explored through various models, such as the Standard Model, which describes how these forces interact with different types of particles, including fermions, which make up matter, and bosons, which mediate the forces. The fundamental forces are represented by force carrier particles. For example, photons are the carriers of electromagnetic force, while W and Z bosons are responsible for mediating the weak force, and gluons carry the strong force. Understanding these relationships helps scientists to explain phenomena ranging from the behavior of subatomic particles to the dynamics of galaxies. Research in particle physics not only enhances our understanding of the universe, but also informs technology and innovation, as concepts developed in this field have led to advancements in medical imaging, energy production, and materials science observational evidence in astronomy. Understanding the universe, it encompasses the data collected through various means, including telescopes, space probes, and other instruments that allow scientists to study celestial objects and phenomena. One of the most prominent examples of observational evidence comes from the Hubble Space Telescope, which has provided breathtaking images of distant galaxies, nebulae, and other cosmic wonders, revealing details that were previously invisible to us. The light from these distant objects, often traveling billions of years to reach us, allows astronomers to learn about the age, composition, and behavior of the universe, and even its expansion. Another significant source of observational evidence is the study of cosmic microwave background radiation, which is essentially the afterglow of the Big Bang, filling the universe with a faint glow, detectable from any point in space. This radiation offers a snapshot of the early universe, providing insights into its origins, structure, and evolution. The European Space Agency's Planck satellite has played a key role in measuring this radiation, offering data that help refine our understanding of cosmology. Furthermore, the observation of gravitational waves, ripples in space-time, caused by cataclysmic events like merging black holes or neutron stars, has opened up a new realm of astronomy. Detected for the first time in 2015 by the LIGO Observatory, these waves confirm predictions made by Einstein's general relativity and provide a new way to observe the universe, allowing scientists to gather evidence about phenomena that were previously undetectable through traditional methods. Planetary exploration through missions like NASA's Mars rovers also contributes to our observational evidence, offering detailed imagery and data about the Martian surface, atmosphere, and potential for past life, as well as the search for water on other celestial bodies. Understanding the possibility of life beyond Earth, observations of exoplanets, or planets outside our solar system, have surged in recent years thanks to missions like Kepler and TESS, revealing an astonishing variety of worlds, some located in the habitable zones of their stars, where conditions could be right for life. Techniques such as the transit method, where a planet passes in front of its star, causing a temporary dimming, provide evidence of these distant worlds, enriching our understanding of planetary systems and their formation. Additionally, the study of supernovae, especially type Ia supernovae, serves as a crucial observational evidence for understanding the rate of expansion. Astronomical phenomena can often hint at the existence of new forces or principles that govern the universe, and scientists observing the cosmos for signs of these intriguing occurrences. One such phenomenon is the behavior of galaxies, particularly when they appear to rotate faster than expected. According to the laws of gravity, galaxies should rotate at certain speeds based on the mass of the visible matter within them. However, many spiral galaxies, such as our Milky Way, exhibit rotation curves that suggest there is far more mass present than can be accounted for by stars, gas, and dust alone. This discrepancy has led to the hypothesis of dark matter, which is thought to exert gravitational influences. But its exact nature remains one of the great mysteries of modern astrophysics. Another fascinating example comes from the observation of gravitational waves, ripples in space-time caused by massive accelerating objects, such as colliding black holes or neutron stars. The detection of these waves, first confirmed in 2015 by the LIGO Observatory, confirmed predictions made by Einstein's general theory of relativity, but also opened the door to understanding how gravity behaves under extreme conditions. The study of gravitational waves may reveal insights into previously unknown aspects of gravity, or even suggest new forces that operate under specific circumstances. Supernova, the explosive deaths of massive stars, are also critical astronomical events that can provide clues about fundamental forces. When a massive star exhausts its nuclear fuel, it may collapse under its... The light curves of these explosions, which describe how their brightness changes over time, can vary greatly depending on the underlying physics at play. The study of these light curves can reveal new insights into the forces involved in stellar evolution, nuclear reactions, and the dynamics of matter under extreme conditions, potentially indicating the influence of forces beyond our current understanding. Cosmic rays, high-energy particles that travel through space, are yet another mystery that may hint at new forces. These particles, which originate from sources like supernova or active galactic nuclei, have energies that sometimes exceed what we can produce on Earth. The mechanisms that accelerate these particles to such high energies could involve unknown forces or interactions, pushing the boundaries of our current physics and leading to theories that extend beyond the standard model. The cosmic microwave background radiation, a faint glow left over from the Big Bang, also offers clues to the fundamental forces in the universe. Variations in temperature and density in this ancient light can provide insights into the early universe, dark matter, and dark energy. Two of the universe's most mysterious components have puzzled scientists for decades, leading to intriguing questions about their nature and potential connection to undiscovered forces. Dark matter which makes up about 27 of the universe's total mass and energy content, cannot be seen directly, as it does not emit, absorb, or reflect light. Instead, its presence is inferred through gravitational effects, such as the way galaxies rotate or how light bends around massive objects. This elusive substance seems to be responsible for holding galaxies together, preventing them from flying apart due to their high rotation speed. On the other hand, dark energy thought to be driving its accelerated expansion. Unlike dark matter, which exerts gravitational attraction, dark energy seems to have a repulsive effect, causing galaxies to move away from each other at an increasing rate. Given their mysterious properties, scientists speculate that dark matter and dark energy might be related to undiscovered forces or particles, potentially reshaping our understanding of physics. Some researchers propose that dark matter could be linked to new types of fundamental particles, which might interact with ordinary matter in ways that we have yet to understand. For example, the weakly interacting massive particles, or WIMPs, are a leading candidate for dark matter, and their discovery could point towards new physics beyond the standard model. Furthermore, the relationship between dark energy and gravity raises questions about the forces at play in the universe. Theories such as modified gravity suggest that what we perceive as dark energy might actually be the result of an alteration in our understanding of gravitational forces over large distances. This could imply that there are additional forces, perhaps akin to those found in quantum physics, which have yet to be discovered. Some physicists explore the idea that a fifth fundamental force, beyond the four we currently know, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, could exist and play a significant role in the dynamics of dark matter and dark energy. Moreover, the search for a unified theory that can incorporate both quantum mechanics and general relativity might reveal connections between these dark components and undiscovered forces. String theory, for instance, posits that there are additional dimensions beyond our familiar three-dimensional space, which could harbor hidden forces or particles influencing dark matter and dark energy. As researchers delve deeper into the cosmic microwave background radiation, gravitational waves, and other astronomical observations, they hope to uncover clues that in recent years scientists have reported several intriguing anomalies in cosmic ray observations, which have led to about the potential existence of new forces or unknown physics. Cosmic rays, which are high energy particles originating from outer space, mostly consist of protons, but they can also include heavier nuclei and electrons. These particles travel across vast distances, and when they collide with the Earth's atmosphere, they create a cascade of secondary particles which can be detected by ground-based observatories or satellites. One of the significant anomalies was observed by the Alpha Magnetic Spectrometer, a particle physics experiment module mounted on the International Space. This experiment has detected an unexpected excess of positrons, which are the antimatter counterparts of electrons. The detection of these positrons, particularly at higher energies, has sparked discussions about the possibility of new sources of cosmic rays, or even new physics. Some researchers have proposed that these positrons could be evidence of dark matter interactions, while others suggest that they might originate from pulsars, which are highly magnetized rotating neutron stars. Moreover, the IceCube Neutrino Observatory, located at the South Pole, has observed high-energy neutrinos that seem to come from sources outside our galaxy. The nature of these neutrinos raises questions about their origins and whether they could hint at new astrophysical processes or forces at work in the universe. The detection of these neutrinos from cosmic events, like supernovae or gamma-ray bursts, has led to the hypothesis that they could be associated with new types of particles or interactions that we have yet to fully understand. Another intriguing observation comes from the Pamela satellite, which measured cosmic ray protons and electrons and found a discrepancy in their energy ratios. This has led scientists to consider the possibility of new forces acting on these particles, or perhaps even the influence of phenomena yet to be discovered. The idea of a potential new force that could affect cosmic rays is captivating, as it could reshape our understanding of fundamental physics. Additionally, the recent discovery of the so-called knee in the cosmic ray spectrum, where the number of cosmic rays drops sharply at certain energies, has led to new theories about the mechanisms that govern cosmic ray propagation and acceleration. Some researchers are investigating whether this knee could be a sign of previously unknown interactions at play, potentially linking cosmic rays to other areas of physics, like quantum gravity or string theory. These cosmic ray anomalies, while not yet fully understood, open the door to exciting possibilities in astrophysics. They challenge existing theories, gravitational waves, those ripples in space-time caused by the acceleration of massive objects, like merging black holes or neutron stars, play a fascinating role in the quest to uncover new forces of nature. When these colossal cosmic events occur, they create disturbances that travel across the universe, stretching and squeezing. Detectors like LIGO and Virgo have been tuned to pick up these subtle waves, and in doing so, they are not just observing the cosmos, but also opening a new window into the fundamental workings of the universe, which could potentially reveal new forces or interactions beyond our understanding. As scientists analyze the data from gravitational wave detections, they are looking for anomalies, deviations from the predictions made by general relativity, which describes gravity as a curvature of space-time caused by mass. If gravitational waves exhibit unexpected behaviors, it could suggest the existence of other forces or particles, which may not be accounted for in our current models of physics, including the Standard Model that describes the electromagnetic weak and strong nuclear forces. For instance, if gravitational waves from certain events show properties that differ from what we anticipate, it could indicate the presence of extra dimensions, or even new particles, that interact in ways we have yet to understand. Additionally, gravitational waves can help test theories that aim to unify the fundamental forces of nature. Researchers are particularly interested in scenarios that involve modifications to gravity itself, such as those proposed in theories like string theory or loop quantum gravity. These theories suggest that gravity might not be the only force at play, and that our understanding could be incomplete. By studying the characteristics of gravitational waves, scientists could potentially find evidence that supports these new theories. Or, conversely, they could rule them out, refining our comprehension of the universe. Moreover, the echoes of gravitational waves can provide insights into the very early universe, moments after the Big Bang. During this time, different forces may have acted in ways that are no longer observable. If researchers can detect gravitational waves from this epoch, it could lead to breakthroughs in understanding how forces like electromagnetism and gravity came to be as the universe cooled and expanded, potentially revealing how these forces are interconnected. The search for new forces through gravitational waves is still in its infancy. Yet the implications are profound. As detection methods improve, and as we gather more data, we may uncover new aspects of fundamental physics, and perhaps even find completely new forces that govern the behavior of the cosmos. This ongoing research not only enriches the cosmic microwave background, often abbreviated as COOM, is a fascinating relic of the early universe, and its study has opened up a treasure trove of information about our cosmos. Detected as a faint glow permeating the entire sky, the COOM is essentially the afterglow of the Big Bang, providing a snapshot of the universe when it was just about 380,000 years old, allowing us to peer back into a time when matter and radiation decoupled. The fluctuations in temperature and density that we observe in the COOM have profound implications, not only for our understanding of the universe's origins, but also for potential new physics that extends beyond our current models. One of the key ways we can use the COOM to infer new physics is through its temperature anisotropies, which are tiny variations in temperature across the sky, revealing information about the distribution of matter and energy in the early universe. By studying these anisotropies in detail, scientists can test predictions made by inflationary models. Inflation is a theory that suggests the universe underwent a rapid expansion just after the Big Bang, and the patterns we see in the COOM can either support or challenge these models. For example, certain non-Gaussian features in the COOM data could indicate interactions or phenomena that our current understanding does not fully encompass, such as the presence of primordial gravitational waves or other exotic fields. Moreover, the COOM's polarization patterns provide another avenue for exploring new physics. The polarization is a result of scattering processes that occurred during the recombination era, and analyzing these patterns can help us understand the influence of dark energy and dark matter on the evolution of the universe. Any unexpected deviations in the polarization data could suggest new interactions or particles that we have yet to discover, potentially leading to groundbreaking shifts in our understanding of fundamental physics. Additionally, the COMB serves as a powerful tool for exploring the possibility of beyond standard model physics, such as supersymmetry or theories involving extra dimensions. These theories often make predictions about the early universe that can manifest in the COMB's properties. For instance, if certain particles predicted by supersymmetry were produced in the early universe, they might leave imprints in the temperature fluctuations observed today. By comparing the COMB data with theoretical predictions from these models, researchers can identify discrepancies that might hint at new particles or forces at play. The study of the COMB also intersects with the search for cosmic inflation's exact mechanisms and whether the inflationary period itself in the realm of space exploration. Experimental approaches are crucial as they help scientists and engineers test new ideas and technologies before deploying them in real missions. For instance, one exciting area of research involves the use of small satellites or CubeSats, which are compact, lightweight, and cost-effective spacecraft that can be launched in groups, allowing for these satellites enable researchers to conduct experiments on the effects of microgravity on biological organisms, materials science, and even the behavior of fluids, all of which can provide insights valuable for future long-duration missions to the Moon or Mars. Additionally, researchers are experimenting
with in situ resource utilization, which refers to the practice of using materials found on other celestial bodies to support human life and operations. For example, on the Moon, scientists are investigating the potential of extracting water ice from permanently shadowed craters, which could be used for drinking water or even converted into hydrogen and oxygen for rocket fuel, thus allowing astronauts to produce resources locally, rather than transporting everything from Earth, which is incredibly expensive and logistically challenging. Another fascinating experimental approach is the study of astrobiology, which seeks to understand the potential for life beyond Earth. Missions like the Mars Perseverance rover are conducting experiments designed to search for signs of past microbial life on the Martian surface. The rover is equipped with advanced instruments that can analyze soil and rock samples, looking for organic compounds and other indicators that life could have existed on Mars. This research not only enhances our understanding of Mars, but also informs the search for life on exoplanets, which could have conditions suitable for life forms similar to those on Earth. Moreover, the advent of 3D printing technology in space is
revolutionizing how we think about manufacturing in orbit. With the ability to print tools, spare parts, and even components for habitats, astronauts can create what they need on demand, reducing the need for large supply missions from Earth. This experimental approach is being tested on the International Space Station, where astronauts have successfully printed various items, paving the way for more sustainable practices in future space missions, particularly as we consider long-term stays on Mars or the Moon. Then, there are the experimental technologies related to propulsion systems. Traditional chemical rockets, while effective, are limited in their efficiency and capability for deep space travel. Scientists are exploring alternative propulsion methods such as ion propulsion, which uses electric fields to accelerate ions for thrust, offering a more efficient means of travel overlong in the quest to understand the universe. Scientists are continually pushing the boundaries, and one of the intriguing areas of research is the search for new fundamental forces beyond the four known forces of nature: gravitational, electromagnetic, strong and weak forces. To explore these possibilities, innovative, experimental
techniques are being developed, which promise to unlock new insights into the fabric of reality. For instance, one approach involves using particle accelerators, which smash particles together at incredibly high speeds, allowing physicists to probe deeper into the subatomic world. By studying the resulting interactions and collisions, researchers can look for signs of new forces or particles that may not fit within the existing frameworks of physics. Additionally, researchers are experimenting with ultra-sensitive detectors designed to measure extremely faint signals, which could suggest the presence of new forces. These detectors often rely on advanced technologies, such as superconducting materials, which can detect minute changes in energy levels or particle interactions. For example, experiments like those conducted at the Large Hadron Collider have utilized sophisticated detection methods to search for evidence of phenomena like supersymmetry or extra dimensions, which could imply the existence of new fundamental forces. Another fascinating avenue of research is the use of tabletop experiments, which involve smaller scale setups that can test the effects of hypothetical forces in a more controlled environment. These
experiments often utilize precision measurement techniques, such as atomic interferometry, to detect tiny shifts in the behavior of atoms under various conditions. By examining how atoms react to various stimuli, researchers can infer the influence of forces beyond the standard model of particle physics. Moreover, experiments that involve cosmic rays and astrophysical observations are also pivotal in this search. By analyzing high-energy particles that originate from space, scientists can gather information about interactions that occur at energies far beyond what we can achieve in terrestrial laboratories. This cosmic perspective can shed light on potential new forces, as these particles might interact with matter in ways that are not yet fully understood. Researchers are also tapping into the realm of quantum mechanics, exploring the peculiar behaviors of quantum systems to identify any anomalies that might suggest new forces at play. Quantum entanglement, for instance, could be a key area of investigation, as scientists look for connections between distant particles that could imply new interactions or forces. Finally, collaborations across global research institutions are crucial, as sharing data and resources can lead to breakthroughs that individual labs might not achieve on their own. This collaborative spirit is essential in tackling such complex questions, as scientists from different disciplines bring unique perspectives, and particle accelerators are fascinating devices that play a crucial role in our understanding of the fundamental forces that govern the universe, contribute significantly to the exploration of forces in space. At their core, particle accelerators are machines designed to accelerate charged particles, such as protons or electrons, to extremely high speeds, often approaching the speed of light. This acceleration allows scientists to create high-energy collisions, which can generate conditions similar to those found in the early universe, just moments after the Big Bang. By studying the results of these collisions, researchers can gain valuable insights into the forces that hold matter together and govern the interactions between particles. One of the most significant contributions of particle accelerators to the exploration of forces in space comes from their ability to probe the properties of fundamental particles, such as quarks and leptons, which are the building blocks of matter. The Large Hadron Collider, for example, has been instrumental in the discovery of the Higgs boson, a particle that is essential for explaining how particles acquire mass through the Higgs field. Understanding the Higgs boson not only deepens our comprehension of the standard model of particle physics, but also provides critical information about the forces at play in the universe, including the strong and weak nuclear forces, which govern atomic interactions. Moreover, particle accelerators enable scientists to explore phenomena like antimatter, which is the mirror image of ordinary matter. Antimatter plays a crucial role in theoretical physics, particularly in understanding the asymmetry between matter and antimatter. By studying how antimatter behaves under different conditions, researchers can gain insights into the fundamental forces that shape our cosmos, including gravity, electromagnetism, and the nuclear forces. Additionally, particle accelerators contribute to the study of cosmic rays, which are high-energy particles that travel through space and strike the Earth's atmosphere. By simulating cosmic ray interactions, scientists can investigate the effects of these particles on matter and delve into the mysteries of cosmic phenomena, such as supernovae and black holes. This research helps to unravel the complex interplay of forces in extreme environments, where gravity, electromagnetic forces, and nuclear forces converge. Furthermore, particle accelerators are not limited to exploring forces at the subatomic level. They also have applications in astrophysics. For instance, they can be used to simulate conditions found in stars or other celestial bodies, providing insights into stellar formation, energy production, and the fundamental forces at work within those environments. By recreating these conditions in a controlled setting, the Large Hadron Collider, often abbreviated as the LHAAS, plays a pivotal role in the quest to uncover new forces in the universe. It is the world's largest and most powerful particle accelerator, situated underground and built by the European Organization for Nuclear Research, or CERN. The LHAAS was designed to collide particles at incredibly high energies, reaching up to 7 tera electron volts, which allows physicists to recreate conditions similar to those just after the Big Bang, enables scientists to probe the fundamental components of matter and the interactions between them, helping to uncover the underlying laws of physics. One of the key aspects of the LHAAS's mission is to explore the nature of the Higgs boson. Discovered in 2012, this particle is important not just because it fits into the standard model of particle physics, but also because it may point towards new physics beyond our current understanding. Higgs boson gives mass to other particles, and understanding its properties could reveal new forces or interactions that we have yet to discover. In addition to studying the Higgs boson, that is also focused on searching for evidence of supersymmetry, a theoretical framework suggesting that every known particle has a heavier partner. If supersymmetry exists, it could provide insights into dark matter, a mysterious substance that makes up about 20/7 of the universe, but has not been directly observed. Detecting supersymmetric particles could help scientists understand the nature of dark matter and potentially reveal new forces that govern the behavior of these elusive particles. Furthermore, the latest investigates the possibility of extra dimensions, which are theorized in some models of physics. If extra dimensions exist, they could provide pathways for new forces that we do not currently account for in our three-dimensional understanding of the universe. By smashing protons together at near light speeds, the leech creates a variety of conditions where these new phenomena might emerge, allowing physicists to search for signs of new physics, such as unusual particle decay patterns or unexpected energy distributions. As the lake continues to operate, scientists are analyzing vast amounts of data generated from collisions, employing sophisticated algorithms and computational techniques to sift through the information. They are looking for rare events that could indicate the presence of new phenomena and possibly new forces. The collaboration of thousands of scientists from around the world working together at the ET represents a unique opportunity to share knowledge, resources, and expertise. As they pursue the satellite experiments, present an exciting frontier in the quest to understand forces in space. As they enable scientists to gather data from locations far beyond Earth's atmosphere, where traditional ground-based observatories might fall short. By placing instruments in orbit, satellites can measure cosmic phenomena with unparalleled precision, capturing signals and particles that may indicate the presence of previously unknown forces. For instance, satellites like the European Space Agency's Gaia mission, which is mapping the Milky Way with incredible accuracy, provide insights into the distribution of dark matter, a mysterious substance that makes up a significant portion of the universe's masses, yet remains lost by conventional means. These experiments are crucial, as they can reveal anomalies in the gravitational effects on celestial bodies, suggesting interactions that challenge our current understanding of physics. Moreover, satellites equipped with advanced sensors can monitor cosmic rays, high-energy particles that travel through space, and their interactions with the Earth's atmosphere. By analyzing these interactions, researchers can explore the properties of fundamental forces, such as gravity and electromagnetism, in environments that are otherwise unreachable. The detection of unusual patterns or unexpected behaviors in these cosmic rays may hint at the influence of new forces or particles, potentially leading to groundbreaking discoveries in particle physics and cosmology. In addition to this, experiments like those conducted by the Laser Interferometer Space Antenna, or LISA, which aims to detect gravitational waves in space will open new avenues for understanding how forces operate under extreme conditions. Gravitational waves are ripples in space-time caused by massive events, such as merging black holes or neutron stars, and studying them can reveal insights into the fundamental workings of gravity, as well as the nature of space-time itself. If LISA successfully detects these waves, it could not only confirm aspects of Einstein's theory of general relativity, but also expose new aspects of gravitational interactions, thereby shedding light on forces we have yet to fully comprehend. Additionally, satellite missions designed to study the cosmic microwave background radiation, like the Planck satellite, provide a glimpse into the early universe, allowing scientists to investigate the forces that shaped cosmic evolution. By analyzing fluctuations in this radiation, researchers can infer the influence of various forces during the universe's infancy, potentially leading to the identification of new physics beyond the standard model. As satellites continue to evolve, utilizing cutting-edge technology and instruments, the potential for detecting new forces in space expands. Innovations such as quantum sensors, which can measure minute changes in gravitational fields, promise to enhance our understanding of the universe. To identify signatures of new forces in the universe, scientists rely on a variety of advanced detectors, each designed to capture specific types of signals that may indicate the presence of these elusive forces. One of the most prominent types of detectors used in particle physics experiments is the particle detector, which is essential in high-energy physics laboratories, such as the Large Hadron Collider, or LHC. These detectors, including the well-known ATLAS and CAMS, are equipped with sophisticated technology that allows them to track, measure, and analyze the particles produced during collisions at near light speeds. They utilize layers of different materials, such as silicon sensors, gas chambers, and calorimeters, to detect particles like electrons, muons, and jets of quarks, which can reveal the interactions of fundamental forces. In astrophysics, researchers often use telescopes equipped with specialized detectors to observe cosmic rays and other high-energy phenomena. For instance, ground-based observatories like the IceCube Neutrino Observatory employ a unique the faint signals produced by neutrinos, which are incredibly elusive particles. The IceCube detector can help scientists search for signs of new physics beyond the standard model, such as supersymmetry or extra dimensions, by analyzing the behavior and interactions of these neutrinos as they pass through the Earth. Another crucial type of detector is the gravitational wave detector, like LIGO or Virgo, which can sense the ripples in space-time caused by massive cosmic events, such as black hole mergers or neutron star collisions. These detectors use laser interferometry to measure minuscule changes in distance, which can indicate the presence of new forces or interactions that have not yet been fully understood. As scientists continue to explore the universe, the data gathered from these gravitational wave detections may lead to groundbreaking revelations about the fundamental nature of forces at play. Furthermore, scientists also depend on electromagnetic detectors, such as photomultiplier tubes and charge-coupled devices, which are critical in both optical and radio astronomy. These detectors allow astronomers to study distant celestial objects, capturing light and other forms of electromagnetic radiation that can carry signatures of new forces such as dark energy or modified gravity theories. By analyzing the light from supernovae or the cosmic microwave background radiation, researchers can gather clues about how these forces operate on a cosmic scale. Moreover, in the realm of cosmology, balloon, borne, and satellite-based detectors, like the Planck satellite, measure the cosmic microwave background with extraordinary precision, theoretical implications of space exploration and our understanding of the universe, from the fundamental laws of physics to the very nature of existence itself. One of the most intriguing aspects is the concept of dark matter and dark energy. While we can observe their effects on galaxies and cosmic structures, they remain elusive, leading scientists to propose numerous theories, including modified gravity and particle interactions, all of which challenge our understanding of the universe and suggest that there is much more to discover than we can currently perceive. Furthermore, the implications of quantum mechanics, particularly in regards to black holes, have sparked debates around information paradoxes, where some theorists suggest that information may be lost forever in a black hole, while others argue that it is preserved in some form, pushing the boundaries of our comprehension of reality and prompting questions about the fundamental laws governing the cosmos. Another area to consider is the multiverse theory, which posits that our universe may be just one of many, each with its own set of physical laws and constants. This theory, while speculative, opens up profound implications for our understanding of existence, suggesting that there could be infinite variations of reality, each with different outcomes, thus challenging the very notion of what it means to be unique in the grand scheme of the cosmos. The idea of parallel universes also intersects with discussions about the nature of time and space, leading to the intriguing question of whether time travel could ever be possible, and if so, what the consequences might be for causality and our perception of time as a linear progression. Moreover, the implications of discovering extraterrestrial life extend far beyond biology, touching upon philosophy, sociology, and even theology. If we were to find microbial life on Mars, or intelligent civilizations elsewhere, it would compel us to re-evaluate our place in the universe, our understanding of life, and the ethical considerations surrounding our interactions with other beings. The search for extraterrestrial intelligence, often referred to as SETI, raises questions about communication, potential cultural exchanges, and the responsibilities we hold as inhabitants of Earth, especially in light of the potential risks and benefits of engaging with other life forms. Theoretical implications also arise from the study of cosmic inflation, which suggests that the universe underwent a rapid expansion just after the Big Bang, leading to questions about the uniformity of the cosmos and the distribution of galaxies. This phenomenon challenges our understanding of the early universe and hints at a deeper underlying structure, possibly leading to insights about the initial conditions that set the stage. The discovery of a new fundamental force would profoundly reshape our understanding of the universe, opening doorways to new realms of physics and challenging the very foundations of our current theories. Currently, we understand 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, each governing different aspects of. If scientists were to identify a 5th force, it could imply that there are interactions at play that we have yet to comprehend, potentially uniting or further separating the known forces in ways we cannot currently imagine. This discovery might lead to a revision of the standard model of particle physics, which successfully describes 3 of the 4 known forces, but struggles when it comes to incorporating gravity, particularly at the quantum level. Such a revelation could provide insights into the mystery of dark matter, which constitutes about 27% of the universe, and dark energy, which makes up about 68%. These components are critical to our understanding of the cosmos, yet remain largely elusive. A new fundamental force could help explain how dark matter interacts with visible matter, shedding light on its properties, and perhaps even revealing how it influences galaxy formation and behavior. If this new force were to interact weakly with normal matter, it might be detectable through its gravitational effects, or perhaps even through new types of particle accelerators, or detectors designed specifically to uncover these elusive interactions. Moreover, discovering a new fundamental force could revolutionize our understanding of the early universe, particularly during the moments just after the Big Bang. It could introduce new physics that explains why the universe evolved in a way that allowed for the formation of galaxies, stars, and planets. This new force might play a role in cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, and could lead to a deeper understanding of how the universe continues to expand today. The implications would not just be theoretical. They could also lead to practical applications that affect technology, medicine, and energy. The understanding of fundamental forces has historically led to groundbreaking technologies, from the development of semiconductors and lasers to advancements in medical imaging and treatments. A new force could inspire innovations we can hardly envision today, much like the way electromagnetism and nuclear forces have transformed our world. Furthermore, the philosophical implications of such a discovery would be vast. It would challenge our place in the universe and provoke questions about the nature of reality itself. Are there forces or dimensions beyond our current understanding? What does this mean for the laws of physics as we know new forces, if discovered, could significantly reshape our understanding of how matter and energy behave in the vastness of space, opening up possibilities that we might only begin to imagine. Currently, we understand forces like gravity, electromagnetism, and the strong and weak nuclear forces which govern the interactions of particles, the formation of stars, and the dynamics of galaxies. However, if new forces were to be identified, they could lead to entirely new ways of interacting with matter and energy, influencing everything from the formation of planets to the behavior of light across cosmic distances. For instance, let's consider the potential impact of a hypothetical force that operates at very large distances, something that could alter the gravitational pull between galaxies. This new force might lead to changes in the way galaxies cluster and interact with one another. Instead of simply being drawn together by gravity, galaxies could experience repulsion or attraction based on this new force, causing them to behave in unexpected ways. This could result in new structures in the universe, perhaps even more complex than the filaments of galaxies we see today. Moreover, if new forces were to affect how matter interacts at the quantum level, we might see changes in the behavior of particles that make up stars. For example, the process of nuclear fusion, which powers stars, relies on the balance of forces at play within the stellar core. A new force could alter the conditions necessary for fusion to occur, potentially leading to stars that shine in different wavelengths or have different lifespans than those we currently observe. This could influence the production of elements in the universe, affecting everything from the abundance of carbon and oxygen, which are essential for life as we know it, to the creation of heavier elements during supernova explosions. In addition, imagine a scenario where a new force influences the fundamental constants of physics, such as the speed of light or the strength of gravity. If these constants could vary in different regions of space, this might lead to entirely new physical phenomena, where the laws of physics we take for granted no longer hold. This could change our understanding of black holes, potentially revealing new ways they interact with their surroundings, or even leading to new types of celestial objects that we have yet to discover. Furthermore, new forces might also provide insights into the mysterious dark matter and dark energy that seem to dominate the universe's composition. Currently, dark matter is inferred from its gravitational effects, but if a new force were tied to it, we could begin to understand its properties and behavior more clearly. The standard model of particle physics, which has served as the cornerstone of our understanding of fundamental particles and their interactions, is a well-established framework, but, as with all scientific theories, it is always subject to revision and improvement based on new discoveries. If new forces were to be discovered, it would almost certainly lead to a revaluation of the standard model. The model currently describes 3 of the 4 known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, while gravity is described by general relativity, which is separate from the particle physics framework. The introduction of a new force could imply the existence of new particles, interactions, or even mechanisms that have not yet been accounted for. For instance, if a new force were discovered that operates at the same level as gravity, or the other 3 forces, Scientists would need to explore how this force interacts with the existing particles. It could lead to the identification of new particles, similar to how the discovery of the Higgs boson, a crucial particle in the Standard Model, confirmed the mechanism that gives mass to other particles. This would also raise questions about the current unification of forces, which is an ongoing pursuit in theoretical physics. The discovery of a new force could provide insights into how these forces might unify, or it could suggest that our current understanding is incomplete. Considering the complexity of particle interactions, a new force could necessitate not just the addition of new particles, but also a deeper understanding of the underlying principles that govern particle physics. The implications could ripple through various fields of physics, including cosmology and astrophysics, as well as the search for dark matter and dark energy, which are two significant areas that already challenge the Standard Model. Furthermore, new forces might hint at additional dimensions or an extended framework beyond the Standard Model, such as string theory or other theories that attempt to incorporate gravity with quantum mechanics. Each of these scenarios would require substantial adjustments to the theoretical framework. Experimental validation, possibly even a complete overhaul of existing models. This kind of scientific evolution is not uncommon in the history of physics. Many theories, once thought to be comprehensive, have been modified or replaced as new groundbreaking discoveries were made, leading to a richer and more nuanced understanding of the universe. Thus, the possibility of discovering new forces holds the potential to reshape our comprehension of the fundamental nature of reality, opening new avenues of research and inquiry that could lead to revolutionary insights and ultimately deeper connections between the forces that thermodynamics, which govern the principles of energy and heat transfer, are fundamental to our understanding of the universe. But the exploration of new forces could potentially challenge or reshape these laws in ways we are only beginning to comprehend. For instance, the introduction of hypothetical forces, such as those linked to dark energy and dark matter, could have profound implications on how we observe energy conservation and entropy in cosmic events. Dark energy, which makes up about 60–80% of the universe, is believed to be responsible for the accelerated expansion of the cosmos, and understanding its nature could lead to new insights into energy dynamics on a grand scale. Some scientists suggest that if dark energy interacts with normal matter in ways that are not yet fully understood, it could alter our interpretations of the first and second laws of thermodynamics. The first law, which states that energy cannot be created or destroyed, might be challenged if dark energy can somehow be converted into usable energy, leading to a scenario where energy is perceived as flowing in ways we do not currently see. Moreover, the second law of thermodynamics, which posits that the total entropy or disorder of an isolated system can never decrease, might also face scrutiny. In certain cosmological models, particularly those involving the multiverse theory, it is conceivable that different regions of space could experience varying levels of entropy, potentially leading to contradictions with our established understanding of thermodynamics. If new forces are discovered that can manipulate the flow of energy or entropy on a cosmic scale, it could mean that the universe behaves in ways that defy our current laws. Additionally, the possibility of new dimensions or exotic states of matter might introduce new thermodynamic behaviors that we have yet to theorize or observe. The implications of such discoveries would extend beyond mere scientific curiosity. They could affect how we approach everything from energy production on Earth to understanding cosmic events like black holes or the behavior of galaxies. For example, the study of black holes already challenges our comprehension of thermodynamic laws, as they seem to emit Hawking radiation, which suggests they can lose mass and energy over time, yet still preserve the laws of thermodynamics in a broader sense. If new forces introduce additional variables into this equation, it could lead to an evolution of thermodynamic principles as we know them. Furthermore, theoretical physics is exploring concepts like quantum gravity, which attempts to reconcile general relativity and quantum mechanics. This field also examines how forces at the quantum level might influence thermodynamic laws. If the potential existence of new forces in the universe, beyond the four fundamental forces we currently understand, opens up a treasure trove of philosophical questions that challenge our perception of reality, existence, and the very nature of knowledge itself. For instance, if new forces were to be discovered, how would this reshape our understanding of the laws of physics? Would we have to rethink the foundational principles that govern our universe? And if so, what does that mean for the concept of scientific truth, which has long been based on established theories? This leads to deeper inquiries about the nature of scientific progress itself. Is science a linear path to an ultimate truth? Or is it a series of approximations that can be radically overturned by new discoveries? Furthermore, if these new forces interact with matter in ways we don't yet comprehend, what implications would this have for the idea of causality? Could the introduction of new forces suggest a universe that is more interconnected and complex than we have ever imagined, prompting us to reconsider our place in it? Moreover, the existence of new forces could invite questions about the limits of human understanding. Are there aspects of the universe that are inherently unknowable? Or can human intellect eventually grasp all that exists? This touches on the philosophical debate of realism versus anti-realism in science, where the former asserts that an objective reality exists independent of our observations, while the latter suggests that our understanding is shaped by our perceptions, thus potentially limiting our grasp of new forces. If these forces have effects that are not immediately observable, how do we reconcile our empirical methods of investigation with the possibility of unseen influences on the fabric of reality? Additionally, the implications of new forces could also extend to ethics and existentialism. If new forces can manipulate matter or energy in ways we have yet to comprehend. What moral responsibilities might arise from the ability to harness such power? Would humanity be prepared to ethically engage with these forces? Or would our historical tendencies toward exploitation and dominance re-emerge? This could lead to a broader philosophical discussion about the relationship between knowledge and power, asking whether the pursuit of knowledge for its own sake is justified, especially when it may unlock capabilities that could alter life as we know it. Furthermore, the discovery of new forces could provoke thoughts about the nature of existence itself. Are these forces merely extensions of our current understanding? Or do they suggest a fundamentally different layer of reality? One that challenges our definitions of space, time. This can lead to metaphysical questions about when we think about the universe. It's easy to become overwhelmed by its vastness. The sheer scale can be mind-boggling, as the observable universe is about 93 billion light-years in diameter, which is a distance so immense that it defies easy comprehension. To put this into perspective, 1 light-year is approximately 5.88 trillion miles. So just imagining distances on this cosmic scale can be quite challenging for our minds. And yet it's essential for understanding our place in the cosmos. The Milky Way galaxy alone, which is our home, contains around 100 to 400 billion stars and spans about 100,000 light-years across, which means that if we were to travel at the speed of light, it would take us 100,000 years to cross our galaxy from one side to the other. Now, let's consider the concept of galaxy clusters, which are groups of galaxies bound together by gravity. The local group, which is the galaxy group that includes the Milky Way, is just one small part of a much larger structure known as the Laniakea supercluster, which contains about 100,000 galaxies and stretches across roughly 520 million light-years. This immense supercluster is just one of many in the universe, and it highlights the interconnected nature of cosmic structures, as galaxies are not isolated, but rather form vast networks. Moreover, the universe is not static. It is expanding, and this expansion was first observed by Edwin Hubble in the 1920s, when he discovered that galaxies are moving away from us. And the farther away a galaxy is, the faster it appears to be receding. This observation led to the formulation of Hubble's law, which is a fundamental principle in cosmology. The concept of the expanding universe has profound implications, as it suggests that the universe was once concentrated in an extremely hot and dense state, often referred to as the Big Bang, which occurred approximately 13.8 billion years ago. In addition to this, the universe is governed by fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces, which all play crucial roles in the formation and evolution of cosmic structures. Gravity, for instance, is the force that governs the motion of planets, stars and galaxies, causing them to attract one another, while electromagnetism governs the interactions of charged particles, leading to the formation of atoms and molecules. the concept of dark matter new forces. If discovered or theorized, could significantly alter our understanding of cosmic structures, like galaxies and clusters, by introducing interactions and dynamics that we have yet to fully comprehend. For example, the existence of new forces could lead to the formation of galaxies in ways that differ from the gravitational mechanisms we currently understand. These forces might interact with dark matter, which is believed to make up about 27% of the universe, influencing how galaxies form and evolve over billions of years. The introduction of a new force could modify the behavior of dark matter, potentially affecting the clustering of galaxies and altering the balance between the gravitational pull of visible matter and the unseen dark matter that permeates the universe. Moreover, if these new forces were found to operate over cosmic distances, they could reshape our understanding of galaxy clusters, which are vast collections of galaxies bound together by gravity. The dynamics within these clusters could change dramatically, as interactions between galaxies might be influenced by these forces, potentially leading to different rates of galaxy merging and interactions. This could result in a more complex evolution of clusters, where galaxies might either be drawn together or pushed apart in unexpected ways, depending on the nature of the new forces involved. Additionally, such forces could play a role in the behavior of cosmic filaments, which are large-scale structures that connect galaxy clusters across the universe. These filaments are thought to be the backbone of the cosmic web. And if new forces interact with the matter within these filaments, it could lead to enhanced or suppressed flows of gas, affecting star formation in galaxies. If, for instance, these forces created regions of higher pressure or density, they could trigger bursts of star formation, or, on the contrary, inhibit it in different areas, leading to a more dynamic and varied cosmic landscape. Furthermore, the impact of these new forces could also extend to the large-scale structure of the universe itself. Current models of cosmic evolution rely heavily on the interplay between dark energy and gravity, but new forces might introduce additional complexities. They could influence the rate of cosmic expansion, affecting how structures grow and evolve over time. This might help to explain some of the observed phenomena, such as the accelerated expansion of the universe, which remains one of the great mysteries in modern cosmology. In conclusion, the discovery of new forces could revolutionize our understanding of how galaxies and clusters form, evolve, and interact, providing insights that challenge existing theories and models. By exploring the potential effects of these forces, astronomers and physicists can, in the grand tapestry of the universe, new forces could play a significant role in shaping its evolution, introducing complexities that scientists are only beginning to grasp. Currently, our understanding of the universe is largely framed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. However, theoretical physicists are exploring the idea that there may be additional forces, perhaps even forces we have yet to discover, that could influence cosmic events at various scales. One exciting area of research is the concept of dark energy, which is believed to be driving the accelerated expansion of the universe. This mysterious force, which makes up about 70% of the universe, is still not fully understood, and its properties could influence the fate of galaxies, clusters, and the overall structure of the cosmos in ways we are just beginning to comprehend. Additionally, some scientists speculate about the existence of forces that might act at different levels, such as the potential for a fifth fundamental force, which could alter our understanding of particle interactions and cosmic evolution. If such a force exists, it could help to explain phenomena that currently baffle physicists, like the discrepancies observed in galaxy rotation curves, which suggest that some unseen mass, possibly linked to dark matter, is influencing their motion. Furthermore, the interplay between known and unknown forces might also be crucial in the formation of large-scale structures, including galaxy clusters and superclusters, as well as in the early moments of the Big Bang. The gravitational force, for instance, has been the primary driver of matter clumping together to form stars and galaxies. But if additional forces come into play during these formative processes, they could lead to entirely different outcomes in terms of the size, shape, and distribution of cosmic structures. As we delve deeper into the mysteries of the universe, the possibility of new forces could challenge our existing models of cosmology, leading to a more nuanced understanding of the universe's past, present, and future. The integration of these new forces into our theories may help to shed light on unresolved questions, such as the nature of black holes, the behavior of matter under extreme conditions, and the enigmatic properties of dark matter. In essence, the exploration of potential new forces could act as a catalyst for a paradigm shift, prompting scientists to rethink established theories and leading to groundbreaking discoveries that reshape our understanding of the cosmic landscape. As our observational tools, such as space telescopes and particle accelerators, continue to advance, we may find the evidence needed to the discovery of new forces in the universe could profoundly change our understanding of black holes, which have long been some of the most enigmatic objects in the cosmos. Traditionally, black holes are understood through Einstein's theory of general relativity, which describes how massive objects warp space-time, creating gravitational wells from which nothing, not even light, can escape. However, the potential existence of new forces, perhaps related to quantum mechanics, or even beyond our current models, could introduce new dynamics into the behavior of black holes. For instance, if a new force were discovered, it might allow for different interactions between matter and the extreme gravitational pull of a black hole, leading to novel phenomena that we haven't yet imagined. Consider, for example, how such a force could modify the way matter behaves as it approaches the event horizon of a black hole. Current understanding suggests that anything crossing this threshold is irrevocably lost to the black hole's grasp. But if there were a new force at play, it might influence the infall of matter, potentially allowing for some form of escape or transformation of that matter before it is completely absorbed. This could lead to exciting new theories about what happens at the point of no return, challenging our existing models and assumptions. Moreover, the interplay between gravity and any newly discovered force could illuminate mysteries surrounding the information paradox, which questions how information about matter that falls into a black hole can be preserved. If new forces provide alternative pathways for information storage or transfer, it may offer solutions to this long-standing puzzle, suggesting that information is not lost in black holes, but rather transformed or encoded in ways we are yet to fully comprehend. Additionally, new forces
could also impact the formation and evolution of black holes themselves. If we imagine a scenario where these forces influence the collapse of massive stars, we might find that the conditions under which black holes form could be vastly different than we currently believe. This could lead to the discovery of new classes of black holes, each with unique properties that challenge our existing taxonomy, perhaps even revealing intermediate black holes or different behaviors in their spin or charge. Finally, understanding new forces could open up avenues for exploring black holes through different observational techniques. If these forces interact with electromagnetic radiation or other particles in a way that we have not yet discovered, we could develop new ways to detect and study black holes, providing clearer insights into their structure and the environment around them. This could enhance our ability to observe phenomena such as gravitational waves, which are ripples in space-time caused by in the vast expanse of the universe. The fundamental forces, which we usually think of as constants, can behave quite differently, especially in extreme environments like those found near neutron stars. Neutron stars, as you may know, are the remnants of massive stars that have exploded in supernovae, collapsing under their own gravity to form incredibly dense objects. Their gravitational pull is so intense that it significantly alters the behavior of the fundamental forces surrounding them. For instance, gravity, which is one of the 4 fundamental forces, becomes extraordinarily strong in the vicinity of a neutron star. The gravitational field can be millions of times stronger than what we experience on Earth. This intense gravity affects not just the star itself, but also the space around it, warping the fabric of space-time. As a result, the usual rules of physics can seem to bend, making it a fascinating area of study. The immense gravitational forces can lead to phenomena such as gravitational waves, which are ripples in space-time caused by the acceleration of massive objects, like 2 neutron stars spiraling towards each other before merging. Electromagnetic forces, another fundamental force, also exhibit unique behaviors in these regions. The extreme density of neutron stars creates environments where magnetic fields can become incredibly strong, often reaching strengths billions of times greater than Earth's magnetic field. This leads to creation of
magnetars, a type of neutron star with an exceptionally powerful magnetic field. In such environments, charged particles are accelerated to nearly the speed of light, releasing high-energy radiation, including X-rays. This intense radiation can have significant effects on the surrounding space, influencing the behavior of matter and energy in ways that are still being explored by astrophysicists. Additionally, the weak and strong nuclear forces, which are responsible for the interactions between subatomic particles, become highly relevant in these extreme conditions. The strong force, which binds protons and neutrons together in atomic nuclei, plays a crucial role in the stability of neutron stars. In fact, neutron stars are so dense that they are essentially giant atomic nuclei held together by the strong nuclear force, which is competing against gravity. The balance between these forces determines whether a neutron star remains stable or collapses into a black hole. In some regions, especially those near the surface of a neutron star, the interactions between fundamental forces can lead to fascinating phenomena such as the emission of neutron star wind, which is a flow of charged particles ejected from the star. Due to its rapid rotation and the behavior of forces in extreme conditions like those present during the Big Bang is a fascinating subject that combines elements of physics, cosmology, and even philosophy. To theorize about these forces, scientists rely heavily on the principles of theoretical physics, particularly the theories of general relativity and quantum mechanics. During the Big Bang, the universe was incredibly hot and dense, so much so that our current understanding of physics begins to break down. In such extreme conditions, the fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces, are thought to unify into a single force. This concept is part of a grander theory known as grand unification theory, which posits that at very high energies, these distinct forces merge into one. To explore the behavior of forces during the Big Bang, physicists use mathematical models and simulations that extend the laws of physics to these extreme environments. For instance, the equations derived from general relativity, which describe gravity's influence on the fabric of space-time, are used to predict how space and time behaved when the universe was just a few moments old. However, the problem arises when trying to incorporate quantum mechanics into this framework. The Big Bang is thought to have involved quantum fluctuations, which means that particles and forces behave differently than we observe today. The challenge is to create a theory of quantum gravity that can accurately describe these extreme conditions. One of the leading approaches to understanding these forces is string theory, which suggests that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. This theory attempts to unify all fundamental forces, including gravity, within a single framework. Researchers also look into concepts like cosmic inflation, which proposes that the universe underwent a rapid expansion just after the Big Bang, influencing how forces behave. Inflation theory helps explain the uniformity of the cosmic microwave background radiation, which is a remnant from the early universe. Moreover, scientists study the properties of high-energy particle collisions, such as those conducted at the Large Hadron Collider, to gain insights into the behavior of particles under extreme conditions. These experiments allow physicists to recreate environments similar
to those shortly after the Big Bang, providing valuable data on how forces interact at high energies. By analyzing the results, researchers can infer how the fundamental forces might have operated during that pivotal moment in cosmic history. Theoretical physicists also explore the implications of the Higgs field, which gives mass to particles and plays a critical role in how the technological and societal impact of space exploration is profound, influencing many aspects of our daily lives, from the way we communicate to how we understand our place in the universe. One significant example is the development of satellite technology, which has revolutionized global communication, enabling instantaneous connections across vast distances, making it possible for us to use GSEEPs for navigation, and providing real-time weather updates, which are crucial for agriculture, disaster preparedness, and everyday planning. Furthermore, satellite imagery plays an essential role in monitoring climate change, helping scientists to track environmental changes, deforestation, and natural disasters, which ultimately informs policy decisions and raises public awareness about pressing global issues. In addition to communication, advancements in materials science, driven by the needs of space missions, have led to the creation of new materials that find applications in various industries. For instance, the development of lightweight, durable materials used in spacecraft has trickled down to innovations in consumer products, such as athletic shoes, sports gear, and even medical devices. Space agencies like NASA have pioneered technologies such as water purification systems and advanced robotics, which have found applications on Earth, improving healthcare, enhancing safety in manufacturing, and providing solutions in remote areas. Moreover, the societal impact of space exploration fosters a sense of unity and shared purpose among nations. The International Space Station, for instance, serves as a testament to what collaborative efforts can achieve, bringing together scientists and engineers from multiple countries to work towards shared goals, promoting peace and cooperation. This collaboration often inspires younger generations to pursue careers in science, technology, engineering, and mathematics, or STEM fields, thus driving innovation and economic growth. Furthermore, space exploration ignites curiosity, a fundamental human trait that leads to exploration and
discovery. When we gaze at the stars, we are reminded of the bigger picture, encouraging us to think critically about our place in the cosmos and motivating us to protect our planet. The images of distant galaxies and the mysteries of black holes captured by telescopes like Hubble and the upcoming James Webb Space Telescope foster a sense of wonder and keep the spirit of exploration alive. The influence of space technology extends into everyday conveniences, such as the development of weather forecasting and climate monitoring systems, which rely on satellite data. This technology helps us prepare for severe weather events, contributes to our understanding of climate patterns, and ultimately aids in disaster response efforts. Additionally, the advancements in telecommunications, driven by the demands of space missions, have led to global internet access and the rise of smart technologies. The discovery of new fundamental forces could lead to a revolution in technology, sparking innovations that we can only begin to imagine. For instance, consider the implications of harnessing a new force that operates at the quantum level, which might allow for breakthroughs in quantum computing. Currently, quantum computers rely on qubits,
which are fragile and difficult to maintain. If a new fundamental force could stabilize these qubits, or even create new types of qubits that are less susceptible to environmental noise, it would lead to exponentially faster and more efficient computers, capable of solving complex problems in seconds, which would be a game changer for fields such as cryptography, drug discovery, and artificial intelligence. Moreover, imagine if a new fundamental force could influence gravity in ways we have yet to understand. This could open the door to advanced propulsion systems for space travel, potentially allowing us to develop spacecraft that can manipulate gravitational fields, leading to faster than light travel, or at least significantly reducing travel time within our solar system. This would not only transform human exploration of space, but could also facilitate the colonization of other planets, as we could transport resources and people more efficiently. In the field of energy, the discovery of a new fundamental force could yield technologies that allow us to tap into previously inaccessible energy sources. For instance, if we could discover a force that enables us to extract energy from the vacuum of space, we could create devices
that provide unlimited energy. Such a breakthrough would not only solve the energy crisis on Earth, but would also have profound implications for powering spacecraft, habitats on other planets, and even cities in the future. Additionally, if new fundamental forces were discovered that could manipulate the fundamental particles of matter, we could see a new era in material science. Imagine materials that can change their properties on demand, becoming stronger or lighter based on need. This could lead to the development of super strong, lightweight materials for construction, aerospace, and even clothing, increasing safety and efficiency in countless applications. Furthermore, in the realm of medicine, the emergence of new fundamental forces could lead to novel therapies and treatment methods. For example, if a new force could allow us to manipulate biological processes at a fundamental level, we might develop new ways to target diseases, repair damaged tissues, or even regenerate organs. Such advancements could significantly extend human life and improve health outcomes by enabling us to tackle diseases that are currently deemed incurable. The emergence of new fundamental forces could also influence communication technologies. If these forces could somehow be harnessed to create as we look to the future of space exploration, it's fascinating to consider how new forces, both physical and technological, may shape the missions that lie ahead. One of the most significant forces at play is the advancement of propulsion technologies. For instance, ion propulsion systems, which use electricity to accelerate ions, could allow spacecraft to travel farther and faster than traditional chemical rockets. This technology has already been tested on missions like NASA's Dawn spacecraft, and in the future we could see missions that reach distant planets or even travel to the outer edges of our solar system in a fraction of the time it currently takes. In addition to propulsion, emerging technologies in materials science could revolutionize space exploration. Lightweight, durable materials such as graphene are being developed, which could lead to spacecraft that are not only more efficient, but also more resilient to the harsh conditions of space. This could mean longer missions, with less risk of failure due to material fatigue or damage from micrometeoroids and radioroids and radiation. Moreover, the influence of artificial intelligence and machine learning cannot be underestimated. I can analyze vast amounts of data much faster than humans, making it invaluable for navigating space and making real-time decisions during missions. This technology could assist in autonomous exploration, allowing rovers and probes to make decisions on their own. which is particularly important when missions are far from Earth and communication delays can hinder decision-making. Another force influencing future missions is the growing collaboration between countries and private companies. The commercialization of space has opened up new avenues for exploration, as companies like SpaceX and Blue Origin develop affordable launch capabilities, enabling more missions to be launched than ever before. This collaboration can lead to shared resources, technology exchanges, and international partnerships that could enhance scientific research and exploration efforts. Furthermore, the exploration of new celestial bodies, such as asteroids and moons like Europa and Enceladus. These bodies are believed to harbor essential resources, including water ice, which could be critical for future human missions. The potential for mining asteroids for rare minerals and metals could not only support space missions, but also have economic implications for Earth, creating a new frontier for resource extraction. The quest for sustainable life support systems in space is another area where new forces are emerging. As we consider long-duration missions, such as those to Mars, the need for closed-loop life support systems becomes crucial. Innovations in bioregenerative systems, such as growing food in space and recycling waste, could make it feasible for humans' research into new fundamental forces which could extend beyond the well-known four forces of nature. Gravity, electromagnetism, the strong nuclear force. Nuclear force holds exciting potential for technology on Earth. Scientists are continuously exploring the possibility of discovering additional forces, or even new aspects of existing forces, that could change our understanding of physics and lead to revolutionary technology. For instance, if researchers were to identify a new fundamental force, it could lead to breakthroughs in energy generation, particularly in the realm of renewable energy sources. The manipulation of such a force could help create more efficient energy systems, perhaps enabling us to harness energy in ways we have not yet imagined, potentially.
Leading to clean and virtually limitless power sources. Moreover, advancements in understanding fundamental forces could have profound implications for materials science. By comprehending how these forces interact at a fundamental level, scientists might develop new materials with unique properties, such as superconductors that operate at higher temperatures, which would revolutionize industries reliant on electrical power, such as transportation and computing. This could lead to the creation of lossless power transmission systems, drastically increasing the efficiency of our electrical grids and reducing energy waste. In addition, the exploration of new fundamental forces could enhance our capabilities in communication technologies. For example, if researchers can manipulate force interactions at the quantum level, it might pave the way for quantum computing and quantum communication systems that are far more powerful than today's classical systems. This could result in ultra-secure communication methods, as well as significantly faster data processing speeds, transforming how we handle information. Furthermore, understanding these forces could inspire innovations in propulsion systems, particularly for space travel, if we could
harness a new force. It could lead to the development of advanced propulsion technologies, enabling faster and more efficient travel within our solar system and beyond. This could open up new frontiers for exploration, allowing humans to reach distant planets and possibly. Lastly, The study of new fundamental forces could enhance our understanding of fundamental physics, which often has unforeseen technological applications. Just as the understanding of electromagnetism led to the development of countless technologies, from radios to lasers, a deeper comprehension of new forces could similarly lead to unexpected breakthroughs, impacting fields ranging from medicine to information technology. As researchers continue to investigate these possibilities, the implications for technology on Earth could be vast and transformative, fostering a new era of innovation that we are only beginning to envision. Public interest in fundamental physics research could be increased through a variety of engaging and innovative strategies. One effective approach is to enhance the visibility of research findings by making them more accessible to the general public. This could involve simplifying complex concepts and presenting them in a way that captures the imagination. For instance, science communication initiatives, such as public lectures, interactive workshops, and engaging online content, can play a significant role in bridging the gap between researchers and the public. By using relatable analogies, captivating stories, and visually appealing graphics, scientists can spark curiosity and invite people to explore the mysteries of the universe. Another avenue to consider is the integration of fundamental physics into popular culture. Films, books, and television shows often shape public perception and interest in science, so collaborating with creators in these fields to portray physics in an exciting and accurate light audiences and inspire a new generation of scientists. Additionally, involving students and young people in hands-on research projects, summer camps and science fairs can ignite their passion for physics, providing them with first-hand experience in the field. Furthermore, building partnerships with schools and educational institutions can foster a culture of curiosity and inquiry, where fundamental physics is taught not just as a subject, but as a way to understand the world around us. Social media also has the potential to engage a broader audience by sharing bite-sized information behind the scenes looks at research and live culture sessions with physicists. Platforms like Twitter, Instagram, and TikTok can reach a diverse demographic, especially content. Moreover, public exhibitions and science festivals can showcase cutting-edge research, allowing people to interact with scientists and ask questions, creating an environment of exploration and excitement. Engaging storytelling through blogs, podcasts, or YouTube channels dedicated to explaining fundamental physics concepts can also make the subject more relatable and enjoyable, giving people an avenue to delve deeper into topics that intrigue them. Collaborating with professional organizations and advocacy groups can help in organizing outreach programs which would emphasize the importance of physics in tackling global challenges such as climate change and technological advancements, thus making the field feel more relevant and the public